Thank you very much. Can you hear me?
Yes.
Okay. I'm so sorry not to be there, but I'm happy to present you my results about dual agent with Osiris. So, as you know, galaxies form through merging, and as you can see here in this simulation, smaller structures merge together in order to create bigger structures. At the center of each galaxy, there is a supermassive black hole that can accrete, and so when the galaxies start merging one each other, also the supermassive black hole at the center of the galaxies start inspiring one each other. And what we want to study is that phase in which the galaxies have already merged, and so we have only one galaxies, but the two supermassive black holes at the center of the galaxies are not bounded, and so they are two separate sources. These type of systems are important because they can constrain some prediction of the gravitational waves that we expected to see in the observation, for example, with PTA. And because they are the parent population of the system that once they merge, emit gravitational waves. But what it's hard in this project is due to the fact that these systems are very close, but they are very important. In fact, apart from estimate the gravitational background, they are very useful to test cosmological models of formation and evolution of galaxies. So, understanding the properties of this system, we can study which are the processes that drive to the final merger. On the other hand, we want to select multiple systems, but at the beginning, we don't know which is the nature of the second component. So we select AGN, but we don't know which is the other component, and they can be dual AGN, lensed AGN, or a fortuitous alignment of an AGN and a star. So this last type of system is for us is contaminating, but the lensed system for us are a treasure because we can study the intergalactic medium at this small separation, and thanks to this strong lensing, we are able to get information about the lens and probe, for example, the nature of dark matter. So, as I was saying before, this is very difficult because these sources are very close by, and so we need high spatial resolution, and they are rare, so we need large sky coverage. And 2 years ago, the system of this type that were known were very few. As you can see here, we are looking for target with a projected separation below 7 kiloparsec. That means that two agents are the center of the same galaxies. And 2 years ago, we know only 4 systems. So in Florence, Mannucci et al. Discovered a new technique that is able to select multiple systems within the Gaia catalog at separation lower than 0.7 arc seconds. I will not go into details about this technique, but if you want, please ask questions. Thanks to this technique, we are able to select this system. So this system, we know that the primary component is an agent, and some of them has a redshift. The ones that are photometric have not the redshift, and so we observe them with some low resolution spectroscopy in order to measure the redshift and identify if there is a star as a second component. But the main step of our research is to use resolve spectroscopy, like Osiris on Keck, in order to understand which is the nature of the systems. So here I show you an example of some spectra that we obtain with TNG and NTT, so two spectrographs that are not able to resolve the component. So we obtain the spectrum of the sum of both the component, as you can see here in black. And we try the fit with only with only one quasar template in red, and for the source in the middle of the slide, you can see very well that the fit is good only with the quasar template. On the other hand, on the right panel, you can see that we need the superposition of a star in yellow and a quasar in blue in order to fit the data in black. So the red one is the sum of the two components. And as you can see, the stellar absorption that are zoomed in the upper panels are well fitted by the presence of this star. So in this way, we are able to select only the best target. So the system that can be dual or lensed. And so we reject the 80% of those systems that for us are contaminating. So we are using more than one instrument to observe these systems because we need to observe objects in all the sky. So we are using Osiris on Keck to observe the objects in the north part. And for example, Eris on VLT and Muse to observe the objects in the south part of the sky. Here, I show you some of the targets that we observed with Osiris. And as you can see, there are a lensed and dual system. And we are able to understand which is the nature of the system looking at the lines. For example, the third one on the left panel is a dual system because you can easily see that the redshift is not exactly the same. So there is a shift that is calculated and published in the paper of Ciurlo, and also the equivalent width of the line is completely different. While if you look to a lensed system as the second one in both the panels, the equivalent width of the line are very similar, and the redshift is exactly the same. So Osiris is very important because he is able to resolve the system, and we can extract the spectrum from both the component. So the blue square is the part that from which we extracted the spectrum and plotted over here. So we have also other systems that we observed with Keck and not published yet, and also some systems that we observed with Muse and Eris. We observed a lot of systems in these 2 years, and as you can see here, this is the same plot of before, but with our system, and we populate all the region below 7 kiloparsec. And we have also 150 objects approved in the next year. So we will be able to understand the nature of other systems and go on with our statistical studies. In fact, what we are doing now is to, the first step obviously is to fit the spectra in order to, as the first aim, to estimate which is the mass of the black hole. And here I show you the fit with all the components of the H beta on the left, on the H alpha on the right, and then I show you also an example of Muse data in which we will have this redshift because we are talking about the cosmic noon, the magnesium 2 and the carbon 4. So once we obtain the masses, we are able to plot the masses in function of the redshift. And here I plot the masses of the brightest components in blue and the faintest in orange. And the next step that we are working on, and it will be improved in the next year with lots of targets, is to make a comparison with the simulation that we have on the same target selection. And here I show you a preliminary results of a comparison with some prediction made by Ischia Villalba. As you can see, they are very similar. The distribution are very similar. There is a gap here up in the observation, and it is maybe due to the fact that we have some constraint in the selection. Due to the observation constraint, like, for example, the presence of a star nearby. And here, just to conclude, I can show you also a comparison of what we expect about the dual fraction. So now we want to estimate which is the fraction of dual system in function of redshift in order to understand which is the evolution of galaxies. And from our sample of hundreds of objects, we are able to detect how many stars we expected to have, how many lensed systems, and removing them from the pair selection here plotted in black, we can extract the dual fraction in red and compare it with some models. We are now working on it, on this, and we are looking for a comparison with a model that is more similar to our selection technique. And so I leave here, and if you have any question, please feel free to ask me. Thank you.